So you actually see them.
I think I still have to pay my £1,000, spend my £1,000 looking back at my phone. I think that's about time because if I don't spend it, then they will just complicate.
Yeah, I did think about it as well.
Because I had something like £5,000.
I'm so subconscious.
Okay, folks. Today I want to tell you about the slice filtration and the slice spectral sequence. And I thought about beginning the lecture with formal definitions of localizing subcategories and vibrant replacement and things like that, but decided against it. And I want to start by giving you a very down-to-earth calculation, and then show how this calculation feeds into a theory that leads us to the slice spectral sequence and so on. So here's some, let's see, I'll try to make this somewhat self-contained for people who haven't been to previous lectures. But so first I'm going to tell you what a GCW complex is. So let G be a finite group. Now, let me remind you what an ordinary CW complex is. We have a bunch of sets. Now, Kn is the set of n cells. So then you define a sequence of spaces where x0 is k0, and you have a map from Kn cross Sn minus 1 to xn minus 1, and then you have the inclusion of Sn minus 1 into the n-dimensional disk, and then so you have this diagram here. This is usually known as the attaching map. And then the next space in the sequence is the push out of this diagram. So that's a push out. So that's what a CW complex is. Now, for a GCW complex, it's a similar setup, but this time these are G sets. So that is sets equipped with an action of G. And then you have this same diagram, but now the spaces you're constructing are G spaces, and this map is required to be equivariant. You've got a G action on the n-1st space that you've already constructed, and this is the same map as before. There's no G action on the sphere or the disk. The only G action is on the set Kn, and so you have exactly the same diagram, but now all the maps inside are equivariant. So Then, once you've got one of these things, you want to compute with it. And on this side,
Sorry, Doug,
Yeah.
can I just, so really the cells correspond to the orbits in the case, don't they? I mean, if you think
no,
of
well,
a G cell, then it's really indexed on an orbit, not an element of K. I mean,
I mean what I said, Kn is now a G set. Now a G set is a union of orbits, that is
That's
true.
right, yeah,
A G set's a union of orbits. You're taking the Cartesian product of this G set with a sphere. There's no G action, the G action on the sphere is trivial. So it's the Cartesian product of this G set with this ordinary space, and so this is a G space, this is another G space, and this map is equivariant, and then so you take this push out, and then this map will also be
but if you
equivariant.
take an orbit, that in some sense corresponds to a single cell, isn't it? So
Well, your
you can-
decomposable bits are Sn minus ones there, and they're G mod H cross Sn minus ones.
Yes, yeah, so,
Yeah, no, I understand that. It's
That's
just,
what Andy's trying to get at.
okay, so Kn, it's true, is a union, it's a disjoint union of G mod H alphas.
yeah, so
Um,
each of those orbits corresponds to a cell.
Yeah, yeah. And so the action of the group permutes the cells in the manner indicated here. You do not have cells getting rotated. They only get permuted in this description. You do not have the cells, the action on the sphere and the disk is trivial. So in this description, you do not have individual cells getting rotated or anything like that. They are permuted. Now, you can construct.
Sorry,
So
you have to
that's-
repeat that sentence, making clear whether by cells you mean spheres or G mod H cross spheres.
What I mean by
G cells or cells?
ordinary cells. See, if you have a GCW complex, there's an
Yes,
underlying
exactly. Then I agree.
CW
Yeah,
complex,
sure.
and the cells in that ordinary CW complex get permuted by the G action,
Absolutely.
according to the way G permutes the elements of these sets.
But if you think about G cells, then there's only one for each orbit.
Yes.
Yeah.
And
that's why I was
the
talking-
action, so a G cell, if you like, is a union of disks or something, and the action of the group permutes these disks within that orbit. It
Yes.
does not rotate individual disks. That's an important point. All right, now, there's a way to get a chain complex out of this data, and I won't go through the details. I'm sure you know how to do this. So we get a cellular chain complex where the nth chain group is the free abelian group generated by Kn, and there's a certain boundary operator that is constructed in a certain way. I won't go into the details there. Now, if we do the same thing here, because these are G sets, that makes this free abelian group a module over the group ring. Now, one could calculate the homology of that chain complex, and that would also be a graded, ZG module. One could do that, and that amounts to calculating the ordinary homology of the underlying space, and it comes equipped with, the homology itself comes equipped with a G action that is induced by the G action of the space. One could do that, but that's not what I want to do. I want to produce a chain complex of Mackey functors. Now, so a Mackey functor is a gadget that formally it's a functor from the category of G-sets to abelian groups that has certain properties, including one of which is that it converts disjoint union into direct sum. So that means that the value of any Mackey functor is determined by what it does on orbits like this. And so if you know that, you know the whole Mackey functor. And then there are certain, so a Mackey functor is typically specified by saying what it does on each orbit. And then there are certain structure maps relating these things that I don't want to go into in great detail. But anyway, there is a way to get a Mackey functor from a ZG module. And that's what I want to discuss. So there is a functor from ZG modules. And I'll call this functor FP, that stands for fixed point. So what does it do? So let's say M is a ZG module. Then I'm going to get a Mackey functor that I'll indicate like this. And in order to specify this Mackey functor, I have to tell you what it does on each orbit. So it is the following. The value of this Mackey functor on G mod H is, I take my original Mackey functor and
Module?
what?
Your original.
My original module, sorry, my original ZG module. And so this is a ZG module by definition is an abelian group equipped with a G action. As such, it has an H action where H is a subgroup, and you can look at the fixed points of that thing. So you can define this for any subgroup H, and this is the data you need for a Mackey functor. So now the interesting thing about this functor is that it is not exact. This functor is not exact. That is, it doesn't preserve exact sequences. So, whereas the homology of this complex of ZG modules is merely the ordinary homology of the space with an induced G action, the homology that we're going to, when we apply this functor to our chain complex of ZG modules, we're going to get a chain complex of Mackey functors, and that chain complex of Mackey functors is going to have homology of its own, which will be a graded Mackey functor. And that is not the same thing as the fixed point functor applied to the homology. It's different, and it gives you some interesting information. So now I'm going to look at I want to work this out for a very specific example. So the group is C2, and the space that I'm interested in is S and sigma. Sigma here stands for the sign representation. So S and sigma means you have Rn with the sign representation. Let's see, n times sigma. So you have Rn with the antipodal action, and you take the 1-point compactification, and that's S and sigma. And I'm going to calculate its, I'm going to write down this cellular chain complex for it, and I'm going to do the reduced homology. So there is a CW structure, a GCW structure, for which the chain complex is as follows. I'll have a copy of Z in dimension 0. I'll have a copy of ZG, the group ring, in dimension 1. And this is the fold map, or the usual augmentation. Let's see, I want a name for the generator of this group. I'll call it gamma. So this map, the fold map, sends 1 and gamma. They each get mapped to 1 over here. Then there's a map like this. This is multiplication by 1 minus gamma. This is multiplication by 1 plus gamma. And so on. And then you stop it when you get out to dimension n. And you can check that the homology of this chain complex is the same as the reduced homology of the sphere. So if I call this C, then the homology of C is the same as the reduced homology of our space and sigma. And that means that the nth homology group will come equipped with an action of C2, and it'll be multiplication by minus 1 to the n.
Fans of RPN are probably happy to see this.
Okay, but let me point out, this is, the orbit space of this is not RP. This is not SN with the antipodal action. This is the one-point compactification of Rn with the antipodal action. So it has a north and a south pole that are fixed by the action.
You haven't told us how this stopped.
Well, it stops at the nth stage, and the maps are alternately 1 minus gamma and 1 plus gamma until you run out of room.
Yeah.
Okay, now, the orbit space of this is, in fact, the suspension of Rp n minus 1. Okay, now, this is where it gets interesting. So this is a chain complex of ZG modules. I want to apply my functor, this fixed point functor to it, and get a chain complex of Mackey functors. Now, before I do that, I want to give you some notation. The chalk situation here is not great.
There's some on the floor.
Yes, empty boxes, I think.
Well, there's,
Oh, maybe this,
good,
no, this looks
the chalk
promising.
against the wall.
This looks promising.
Yeah.
All right, now,
Oh.
okay, so let me tell you about something called a Lewis diagram. Now, in the case, since our group is C2, the simplest possible non-trivial group, there's only 2 orbits to think about, and that's G mod E and G mod G. And so a Lewis diagram is a picture that looks like this. So these are 2 abelian groups, and there's a restriction map going this way and a transfer map going that way. And I think the rules require that restriction followed by transfer has to be multiplication by 2 up here. Now, so I need to apply my fixed point Mackey functor to this thing. So now I'm going to get a chain complex of Mackey functors. So I will get a diagram, a chain complex of these Lewis diagrams. Okay, so this is the fun part. Okay, so I have to figure out what happens if I do this to Z with a trivial group action. Then I get a Lewis diagram that looks like this. Then if I do it to ZG, the fixed point, I have to find out the fixed point set of ZG, and that's a copy of Z generated. The element in here that gets fixed, that doesn't move, is 1 plus gamma. So this is multiplication by 1 plus gamma. This is the fold map. This is also the fold map. Now, pop quiz. What is this map? It has to make the diagram commute. It's a map from Z to Z. It has to make the diagram commute. What is it? What? Anybody want to guess? Anybody know what?
So far, we have guesses 1 and 2.
Should be 2.
Nobody's guessed 0 yet.
Okay, now I should keep keeping track of dimensions here. Okay, so what does this map have to be?
You
Well,
go
let's-
down across.
So if I take let's take the generator here, see what happens. So down here, I'm gonna get 1 plus gamma, and the image of 1 plus gamma under the fold map is 2. So this has to be 2. All right, now let's do the same thing here. So I can use the same trick. I can take the generator here. It maps to 1 plus gamma here. That gets multiplied by 1 minus gamma here, which gives me 0. So this map is 0, and so on. I'll stop at 4 because I can't have Okay, so this map is 1 plus gamma. This map is 1 minus gamma. This map is also 2. This map is 0. Okay, so this is a so I'm doing this for n equals 4. Okay, so so this is a chain complex of Lewis diagrams representing a chain complex of Mackey functors, and now I want to calculate its homology. So okay, now let me point out that the bottom row is merely the cellular chain complex that we had before, and its homology is the reduced homology of the 4 sphere. So, so it looks like this. That's the bottom row. Now, what about the top row? Look, what's the homology of the top row? This is not hard to figure out. We're going to get a Z mod 2 here. At this spot, we're going to get 0. Here, we're going to have a Z mod 2 again. We'll get 0 here. Now, this is interesting. We're going to get a 0 or a Z here. And what are these two maps? Let me point out that the kernel of this map is generated by the element 1 plus gamma. 1 plus gamma maps to 0 in this map. So that's the cycle here. That's the thing that generates the Z down here, is 1 plus gamma. And it's also the image of this map. So this homomorphism is 1, and this homomorphism is 2. And similar thing will happen for any even value of n. I did it for n equals 4. The same thing's going to happen for any even value of n. Now let's look at it for an odd value of n. Let's do this. Let's do this for n equals 3. So if n is 3, that means that this, we just ignore this last part of the diagram. So here are the dimensions 0, 1, 2, and 3. Okay, so what happens? What happens in the third spot there if, assuming this fourth Mackey functor wasn't there, if we were doing this for n equals 3 instead of n equals 4, then this thing wouldn't be here. So what would we get here? We would get something like this. Now I wrote z minus here because what I mean by that is a copy, let's see, the element 1 minus gamma is in the kernel of this map. The kernel of this map is generated by 1 minus gamma. And how does the group act on 1 minus gamma? It sends it to gamma minus 1. In other words, it multiplies it by -1. So z minus here means z equipped with a non-trivial action of C2. So this is a Mackey functor. Anyway, so the same kind of thing is going to happen for any odd value of n, even n equals 1. And what happened up here is going to so you're always going to get these Z mod 2s, these Mackey functors. You're always going to get these Z mod 2s in even dimensions below n, and in the nth dimension, you're either going to get this Mackey functor if n is even, or this Mackey functor if n is odd. Now, now the interesting part of this, now let me remind you, the bottom row is merely calculating the homology of Sn, the reduced homology of Sn equipped with the group action. And the group action on the top class is multiplication by -1 to the n. So we're multiplying by -1 here, and we're acting trivially here. The bottom row of this diagram is merely the ordinary, the action, the homology of the underlying space equipped with the group action. But the action of the top row is more interesting. It's not, it's more interesting. So here's a theorem about it. HI of Sn sigma evaluated on G mod G is as follows. It's Z mod 2 for I even and I less than n, and so that gives you all these Z mod 2s, and then there's one other non-trivial value, and that's this. So it's Z if I equals n and n is even. And otherwise, in all other cases, it's 0. So that's a description of HI of Sn evaluated on G mod G. Now, I'm going to give names to these generators. Okay, so what I've just calculated, is this. Now, as you know, the homology of a space is also the homotopy of the space smashed with the integer Eilenberg-MacLane space. So this is the same thing as pi I, which can also be thought of as a Mackey functor, of the nth suspension of Hz, the Z2 form of Hz, evaluated on G mod G, and oh no, I meant this. Sorry, I meant this. I meant this. Yes. Okay. All right. So this can be reinterpreted as pi I minus n sigma of Hz. Again, evaluated on G mod G. So we know what this is, at least for non-negative n. Now, I haven't there. You can also ask these kinds of questions for negative values of n, but I won't go into that right now. Okay, so it's described. This group, which I've renamed in various ways, is described right here. Okay, so I want to consider the following. So I want to look at the case where I equals 0, n equals 1. So in that case, if I equals 0 and n equals 1, we're getting a copy of Z mod 2, and and it's related to the following map. This is the sigma sphere, meaning, I can draw a picture of it. This is a circle where the group acts by reflection. And this is its fixed point set, which is the two poles. And this is the inclusion map. And I'm going to give this map a name. I'm going to call this name map A. And the group, so the element in question is, so what is A? So what is A? A is an element, A is an element in pi 0 of S sigma evaluated on G mod G. And there's a Hurewicz map from the homotopy of something to the homology. There's the usual Hurewicz map. And as I said, this is the same thing as pi minus sigma of Hz. And I'm going to use the same notation for the element here and its Hurewicz image. Now, I also have okay, so remember that there was this Z at the top. So we have H2 of S2 sigma. This is Z, and I'm going to call the generator of this group U. The generator of this group. And this is the same thing as pi 2 minus 2 sigma of hz. That's an element U. Then, right, okay. Now, with that in mind, it's possible to name all of these generators. And I can, so I'll see if I can do this. So this one is, now n, for this one, n has to be even. So this is u to the n over 2 is the thing that generates this group. There's a multiplicative pairing here, multiplicative structure, and u to the n over 2 is the element that gives me this z. And this one is u to the I, a to the, or sorry, u to the I has to be even. So I take u to the I minus 2 power, and then I multiply it by a to the n minus I. I think you'll find that's in the right place. Okay, so I've named all these generators in terms of A and U, these two elements that I've defined here. And let me point out, A is actually an element in the equivariant homotopy groups of spheres, and we're looking at its Ravenel image, whereas U only lives in the homology, in the homotopy of HC. Now, I would like, now, so far I've been, the example I've been, the GCW complex I've been discussing is Sn sigma. Now, let rho stand for 1 plus sigma. This is the regular representation. Of C2. So this is a two-dimensional representation that where the group swaps two basis elements, and it's isomorphic to 1 plus sigma. So we can say that H, the reduced homology of this is the same because of this because rho is 1 plus sigma. You can say that you have an isomorphism like this, Mackey functors. This is reduced homology. Smashing with a sphere with trivial group action just suspends things up and down. Nothing funny happens. Okay, now let's get NU into the picture. Okay, so recall there is a C2 spectrum known as MUR, and this is the ordinary. So if you ignore the group, it has a C2 action on it. If you ignore the C2 action, it's the tome spectrum for complex cobordism. It's the usual complex cobordism spectrum, MU. And that R is supposed to remind you that there's a C2 action. Now I'm doing some serious hand waving here. There's a lot of details that have to be checked to actually make sense out of this, but roughly speaking, C2 acts by complex conjugation. You know how to build the spectrum MU from tome spaces MUN, and MUN is something that's defined in terms of complex vector bundles, complex Grassmannians, and so forth. And there's this, and you have a C2 acting by conjugation. You have everything inside can be conjugated. And that's how you get the action on the spectrum MU. Now, there are maps SN rho, I'm going to call the mass RN bar and MU bar, such that the underlying mass now, if I ignore the group action here, this would be S2N, and this would be MU, and I will call the underlying map Rn without the bar. And these are polynomial generators for the homotopy of MU. And it's known that you can lift these in the equivariant setting. You get a map from SN rho into MUR that does the right thing. Now, we know classically that if you kill all of the positive dimensional homotopy of MU, what do you have left? You have HZ. Now, there's an equivariant analog of that fact. Now, before I do this equivariantly, let me give you a fancy way of saying that. Let A stand for, now this is notation, it's going to sound a little peculiar first. So this looks like a polynomial algebra. This is my notation for the sphere spectrum. So what I mean by this is an appropriate wedge of spheres. This is in the stable category. It's an appropriate wedge of spheres, and it comes equipped with an associative multiplication. It's not commutative. Even though it looks like it should be commutative, it isn't. That's another story. But it's this is an associative ring spectrum. And there is an interesting map from this to MU that does exactly what you think it does on the various summands. The summands, this is a wedge of spheres indexed by monomials in the R's. And if you have a monomial in these R's, there's a summand in this spectrum corresponding to it. You map that into MU in the obvious way. And so you get a map. This is a map of ring spectra. In other words, MU is an A module. Now, there's another map that I'm interested in. And that's the map to the sphere spectrum that sends all the positive dimensional summands in here to 0. Just projects onto the bottom summand. Now, with that in mind, we can do the following. So let's see, I want to give these names maps, or maps names, so what should I call them? For lack of imagination, I'm going to call these alpha and epsilon. Okay, now let's consider this. Let's consider this. Let's take the smash product of mu with A with the sphere spectrum. All right, now I have let's see. Do this. I can use the multiplication that mu is a commutative ring. I can use the multiplication on it to produce a map from mu smash A to mu. And so what will I call that? Let's call it alpha tilde. Okay, so I can take alpha tilde smashed with the sphere spectrum on this side, and that gives me a map to mu smash the sphere spectrum, which is the same as mu. And I can also use this map epsilon to get a different map to the same thing. So I've got two maps from here to here. Then I can take the co-equalizer, and I'll denote that like this. So this is the co-equalizer. Now, this amounts to killing all the higher homotopy groups. Going from here to here amounts, or going from mu to here amounts to, I guess I could also do this. Going from here to here amounts to killing all the higher homotopy groups in mu. And we know what happens when you do that. You end up with the Ellenberg-McLean spectrum. This is a very convenient way of saying that. Now, we can do the same thing in the equivariant world. So remember that it's known that these maps, these generators of these polynomial generators of the homotopy of mu have equivariant counterparts that are maps from Sn rho to mur, and we can do precisely the same construction that we did on this board. We can do we can imitate that. Everything on this board can be imitated in the category of C2 spectra. And so let's say A bar is the polynomial on R1 bar, R2 bar, etc. So this is a wedge of Sn rows. And you can do the same thing that we did over here, and you can do the same thing. You can form a co-equalizer as before. And then the theorem is that when we do this, what we get is still the equivariant form of the integer Eilenberg-MacLane spectrum.
That Mackey functor is the one that has, what are the restriction and transfers in it?
This.
Okay.
Okay, so this same thing works equivariantly. Now, it requires a more subtle proof. And analogous statements hold if you replace MUR, if you norm it up to some bigger group, some bigger cyclic 2 group, the same thing happens. And this has a name. This is called the reduction theorem. Now, for the case C2, which is the one I've been discussing, this is due to Hu and Kriz. Did it in a 2001 paper. And there is a C2 to the n analog. Due to HHH. Now, we can manipulate this construction a little further and get an analog of a Postnikov tower for MUR. Now, since I'm almost out of time, I'm going to, maybe in the next lecture, I'll say more about how to do that. But for now, let's just say one can manipulate this to get an equivariant analog of the Postnikov tower. In which the following happens. The nth layer of this, which I'm denoting like this for reasons that I'll explain in the next lecture, is as follows. It's contractible for n odd. And for n even, it's a suitable wedge of copies of S n rho over 2 smash hz for n even. Now, how many wedge summands are there? It's the number of monomials in the polynomial ring. It's something you can count. It's actually the related, it's the partition function of n over 2. Anyway, you get a, so this leads to a spectral sequence converging to the homotopy of MUR as a Mackey functor. And the input is the homotopy of these things as Mackey functors, which is what I calculated earlier in the lecture. So the calculation of the first part of this lecture gives you the input, the homotopy of this thing. And that is the input for this spectral sequence that converges to the homotopy, the full equivariant homotopy of MUR. So, the E2, let's see if I can get this right. The E2 of S V of this thing is pi, now this is a spectral sequence of Mackey functors, pi, I need the E1 term, pi V minus S of P, dimension V, dimension V. And this converges to pi V minus S mu R. These are all Mackey functors. This is a spectral sequence of Mackey functors. Now, V here is understood to be an element of ROC2. This is an ROC2 graded spectral sequence. Now, anyway, this is a spectral. This is the slice spectral sequence, and it's. I'll have to see. I've run out of time. So that's the end of the lecture. Thank you.
So is this all going on in the world of MUR modules?
Yes, it is.
So
Yes, it
the
is.
site is,
Yes, it's going on in the world of MUR modules.
it's only associative, not.
What?
MUR is not a commutative object?
The MUR is
It
commutative.
is-
These A's are not commutative. They're known as twisted monolith rings.
Yes, right.
They're associative, but they're not commutative, even though the notation makes it appear that it's commutative. They're not commutative.
They sort of look at homotopy associative. How do you show they're actually associative?
You can construct them in such a way that they're actually associative. You can do the, what do you do? Take let's see, suspend your favorite sphere and take its loop space, and then tomify the appropriate thing. So, so this A is a smash product of tomified loop spaces, like I said. Loops of suspension of a sphere, and that's a strictly associative gadget.
And can you do this construction by just killing homotopy? Which is how you would normally do a post-Minkov construction.
Well,
non-concurrently.
okay, see, if you were to, you could set up this spectral sequence that I just wrote down, you could set that up in the non-equivariant case, the classical case, where there's no group action. You could get something called the Postnikov spectral sequence. Now, why have you never heard of the Postnikov spectral sequence? It's because it's useless. The input is the homotopy of the thing you're trying to compute the homotopy of. So so in the classical case, this is you could make this spectral sequence, but it wouldn't give you anything useful. Here, it's interesting. What?
Postnikov tower is not entirely useless, but yeah.
No, but you have to know, in order to set up this spectral sequence, if you want to know what the E2 term of this spectral sequence is, you have to know all the homotopy groups, and you don't in general. But in this case, let's see, in the classical case, the nth stage of this thing, the thing I'm calling PNN, is an Eilenberg-McLean space that picks up the nth homotopy of the space you're interested in. And you need to know that ahead of time if you're going to run this spectral sequence.
Yeah. I'm not really asking about whether you can calculate it. I'm asking whether there's a theoretical construction.
Okay, I'm trying to answer that in a roundabout way by saying that these building blocks, the thing that makes this interesting is that these building blocks are things like this. And as we saw, their homotopy is not concentrated in a single dimension. They have homotopy in various, up to dimension n, they have homotopy in dimensions 0 through n. Various things happen. So there's something interesting going on in this spectral sequence. So I'm going to say more next time about exactly how this is constructed formally. But it's not merely killing homotopy groups because of the fact that these things have more than one non-trivial homotopy group. So it's more subtle than
So is there some sort of T structure involved?
Yes, there is a T structure, exactly. There is a T structure, and I will describe it next time. Now,
Sorry, I didn't mean to make you do the next lecture.
no, it's a good transitional question. I'm going to show this. Are there any other questions before I talk about scheduling? Yeah.
And you said there's a C to the analog.
Yes, there is. And
So you get the normed up on like playing making function?
you get, well, then you have to deal with Mackey functors for C2 to the N. So they have more complicated Lewis diagrams. And there are more complicated, and the ingredient, and this gets replaced by something more complicated that I can describe next time. But you can do all that. And that's exactly what we do. And this is the main computational tool for proving the theorem. Now, I've limited, in this case, I've limited to the group C2 to keep it simple, but you can do it for bigger cyclic groups. But the input and output are more complicated. Okay, now I'm going to turn this off.